So trigonometry, and in fact, for those who are doing the course as Gaeilge, when you're in All-Irish School, there are some of the chapters that are particularly difficult. Not for the maths, but the terminology is, there's loads of it in trigonometry. And just the terms, so apologies if the terms are a little bit throwing you. But this is actually online as well as Gaeilge. So, but trigonometry is about triangles. A triangle is something with three sides, three angles, and we also do a tiny bit on sectors here, circles with a little bit out of them. Okay? So part one of this session is about trigonometry definitions and right-angle triangles. It's really about the questions that are all about right-angle triangles. The trigonometric functions, what sine, cosine and tan are, the inverse, the right-angle triangle toolbox. What I hope to present is a set of tools that you can use to solve anything in right-angle triangles. Just as a plumber or a plasterer or an electrician will carry a set of toolboxes, screwdrivers, hammers, etc., phase testers, whatever. When you're solving right-angle triangles, you've got your toolbox. This toolbox will solve the question for you. It'll solve every single question type on the syllabus, and it's quite a small toolbox, but you have to get used to using it well. Some related work examples, and then some compass directions, north, south, east, west, and how people in sailing talk about angles in a different frame than we do. So that's what this session's about. So terminology. You can describe triangles by their relative lengths of their sides. This is an equilateral triangle. Three sides the same, three angles the same. And that's shown here by the dash there, the one line here that's showing it's the same. The 60, 60, 60. And that could have been shown here as well by two dashes. An isosceles triangle has two sides the same, marked by the two dashes. And the scalene is different. It's showing that every one of the sides is different, 1, 2, and 3. And every one of the angles is different, 1, 2, and 3. So there's nothing there that's common. So that's not particularly great. You can also define angles by triangles by their internal angles. So for example, this is a right angle triangle. It's got a 90 degree. This is an obtuse, more than 90. And this one here, they're all less than 90. We're going to talk about right angle triangles. The right angle triangle has three sides, and the hypotenuse is the side that is opposite the 90 degree. That's its definition. The hypotenuse is the big one. The other A and B are the other sides. This is really, really important. You can call the sides of a triangle A, B, and C in any order you wish. You can call this one A, this one B, or this one C, or change them any way you wish. Doesn't matter. But once you do, the angle opposite it must have the same letter. So capital A must be associated with A, capital C must be associated with C, and in the other one, the B there, the angle B must be associated with the side B. So that's what it means. So the angle is always opposite the side with the same name. Is that okay? The angles we call A, B, and C. We're using capital letters with the symbol there for angle, and the sides we're calling A, B, and C. The order doesn't matter, but make sure they're opposite each other. Otherwise, all of the equations throughout the whole trigonometry book, formulae, everything you learn don't make sense. Okay? Now, these are right-angled triangle characteristics, and they say that a right-angled triangle has three angles, and the angles add to 180. And also, Pythagoras' theorem says that this side here, squared, plus this side squared, gives you this side squared. And that's Pythagoras' theorem, a long time ago discovered. Now, we then define trigonometric functions. And a trigonometric function is like only, here in this case for right angle triangles, we take an angle and we say this angle here, we define sine, cosine and tangent. Now what are they? The sine is defined as opposite over hypotenuse, cosine is adjacent over hypotenuse, and tan is opposite over adjacent. But what does all this mean? Well, let's start with the angle A. If this is the angle A, and this is my center of focus, then everything starts from this. A, I draw a line opposite it to its linked letter, and this by definition becomes opposite. That's opposite for A. The 90-degree one here defines the hypotenuse. And there's only one left. So this must be the adjacent. So always start with the angle you're given. Draw a line opposite it. That defines opposite. The 90 defines the hypotenuse. And the other one is the one that's left. Is that okay? So in this case, going back to these equations that we did here, we're saying that the opposite is A, because we started with A, because we're looking at A. And therefore the others are defined. Now, the sine is defined as opposite over hypotenuse. Opposite over hypotenuse would be A over C. That's the sine. Cosine is adjacent over hypotenuse. Well, the adjacent for A is B over C. And the tangent is opposite over adjacent. Well, that's the opposite over adjacent. It's A over B. Now, to learn these things about sine, cosine, and tan, so, cos, ca, toa, American textbooks, very sorry. Some old hag cracked all her teeth on asparagus. Irish textbooks, just as bad. Oh, heck, another hour of algebra. Really lame stuff, really pathetic. But there are better ones, but, you know, it's just, they're there. Now, let's look at the angle B. Remember that the triangle doesn't have to start with there. They can give you a triangle where the angle you're looking for is there, or they may have turned the angle around, or around like this, or any shape. So what you do is you say, what's my focus? We're asked about angle B. Well, what's the rule? The rule is you go to where you're looking for first. You draw a line from it to the side, and that defines the opposite. Because for this question, I'm interested in B. That is the opposite. It may be like that. It may have been drawn like this or like that, but that's the angle I was looking for. I'm considering angle B. If that's B, I look for the 90 degree, and the 90 degree opposite it defines the hypotenuse. And the only one that's left then must be the adjacent. And now I use the same formulae. So if I want to get the sine of something, like sine of B, well, what is sine of B? Well, sine of B, well, sine of anything, is opposite over hypotenuse. So, sine of this is B. Well, it's that over that. Or in this case, it's B over C. If I want the cosine of B, I go to cosine. What's cosine? It's adjacent over hypotenuse. Adjacent of B, well, that's the adjacent. That's A over hypotenuse. That's C, A over C. And if I want the tan of B, I say, well, the tan is opposite over adjacent, but, oh, opposite is here. Adjacent is that, it must be B over A. Okay? So, it doesn't matter how they throw the triangle. Find the angle, draw the line, call it opposite, the other's hypotenuse, then plug in the formula. Is that okay? It's done. Now, inverse trigonometric functions. What are they? Well, this is really about English, really, more than anything else. about a long way around of saying something. Just imagine we have this angle theta here, theta, and it's saying that the sine of it, the sine of theta is 5 over 13, because this would be the opposite. This would be the hypotenuse because that's 90, and this would be the adjacent. So the sine here is 5 over 13. Sine theta is 5 over 13. In English, they say sine theta is 5 over 13, or theta is the angle that has a sine of 5 over 13. Or the inverse of sine over 13 would give you the angle. So that's how they write that. Sine theta is 5 over 13, theta is this. Now, that's how they would say it in English. We might be more used to doing it mathematically and saying that sine of theta is 5 over 13. But I just want theta. And how do I get rid of theta on this side? What gets rid of a sine for me? What's its twin? Inverse sine. So inverse sine, 5 over 13. And we know that they cancel because that's why I chose them. So I know that theta is equal to inverse sine 5 over 13. If I type in 5 over 13 in a calculator and hit the inverse sine button and the degrees are on, I'll find 22.62 is my angle. And that's how I get inverse trigonometric functions. Similarly, if I started with cosine of this, I would have gone for the opposite, adjacent hypotenuse. I would have labelled it. And then I said, but cosine is adjacent over hypotenuse, so it's 12 over 13. How do I get rid of a cosine? Multiply by inverse cosine. Theta is the angle that is an inverse cosine of that. 12 over 13, inverse cosine, same angle. Tan, 5 over 12. Getting rid of a tan, inverse tan. And then 5 over 12, inverse tan in your calculator, 22.62. And that's it. So you can see there how I manipulated trigonometric functions. If I didn't like sine theta and my focus was just on theta, I just creamed it by putting in a sine minus beforehand, inverse sine. With the inverse sine, I took the inverse sine of all of this and the inverse sine of all of that. They cancelled. I was left with the theta. This might look messy, but it's just a number. A number divided by a number, function inverse sine, no x's, no thetas, no variables, just the answer. If I had started with the inverse sine, and I wanted to get rid of it, I would have multiplied by sine in front of it, the sine of it, to get the sine of that. They would cancel. 5 over 13 is sine of 22.62. So that's the way that would work. Okay? I'll take a break for a second. I'm just wondering, Christine, are there any more pages on the way? These are pretty warm. I thought I'd run a few, but actually I didn't realize they were all gone. So I do know what's coming. It's just that it's not an A3, so apologies. Just wait. You have it in front of you there, don't you? But we're just waiting for the hotel to photocopy onto A3. Once again, I'll cut that bit out of the video as well. That's great. Thanks a lot. That's great. Super. Thanks a million. Thanks, Christine. I'll just continue with that. So, if we look now at trigonometric functions for cosine, it's exactly the same. So the cos of an inverse cos gets rid of it. The inverse cos of cos gets rid of it. So these are just the pairing of two similar functions, just like addition and subtraction. Same for the tan and the inverse tans. Now I'd like your attention for this. What I'm going to approach now is a general problem solving method of solving all trigonometric functions. Okay? I'll start this in a second, but this actually arose out of the sessions in maths that I gave in Cork and Limerick. What happens is each year you do something and then you find that somebody doesn't get it, or there's a confusion there, or you know yourself it's not explained well, you know in the audience it's not right, or there's something just not clicking. And this came out of one of those sessions about 2 years ago, and I think that for the first time I've actually written it up. I hope it works. Hope it works for you as a method. It works nicely. So I'm going to start. Okay, let's look at right angle triangles. I'm going to use a general problem scenario for all triangles. And if we think about a typical structure for the moment, a triangle is made up of 6 parts. There are 3 sides and 3 angles. I'm going to call the angles A, B, and C, and the sides A, B, and C. And in any question you'll ever be asked, you're asked to find something they're not giving you. If all of the 6 values were known, if you knew the 3 angles and the 3 sides, the question is done. You just read the answer. What they're trying to say is, well, if you know 2, could you figure out the 3rd? So what I've done here is I've shown this grid with ABC and ABC beside it, and where I know something, I put a tick. So in this case, I might know a few things, but I don't know the B and I don't know this B. There's loads of things missing. And I'm trying to turn that into something where I know everything. All the boxes are ticked. In this particular set, they'll always have a C of 90 here. So we're dealing with the right angle triangles, okay? So let's look at Pythagoras now. Here's a question. C squared is equal to A squared plus B squared. How do we actually figure out that? The question is, find the 3rd. So if we look at it, we can say we know 2 of the sides. We've got a B here. Something funny. No, this is fine. Sorry, I'm just wondering what versions of paperwork I'm on here. So apologies for that. Okay. You see these tiny little boxes here that show up? They're actually not on the computer screen because they're covered, and they're printing out in these particular shots. But that's my issue there. It's my fault. I should have spotted that in PowerPoint. PowerPoint shows it one way but keeps a different print behind it. So ignore those tiny little boxes. Is that okay? They're just covering up numbers that show up later. Okay, so we're going to use this general problem scenario where we're going to try and fill in the grid each time. So the first question starts is, you're given 2 sides and you're asked to find the 3rd. So that's 10 and that's 8. How do we actually find out what the answer is? So you've got a triangle now. One is 8, and the other is 10. What's this one here? Well, to do all of these questions, what I do is I say, what's in my toolbox? We're going to keep this page steady for all of the right angle triangles. Our toolbox, the only toolbox we have, is it says that all of the angles add to 180. Pythagoras says that one of the sides, the hypotenuse squared, is equal to the sum of the other two sides squared. And we also have the trigonometric functions. So, okay, can we solve this question then? If we know that's a 10 and that's an 8, can we use the first rule? Can we use all the angles adding to 180? Well, do we know the other angles? We know that this is 90, but we don't know the other two. Is that okay? It looks like we don't have that information. We've only one of the angles. Is that okay? If we've only one of the angles, we can't figure out the other two, can we? Because that could be 45 and 45, or 60 and 30, or 80 and 10, couldn't it? So we're sort of stuck there. So how do we get there? Okay. Well, how do we get here with the 8 and the 10? Could we use the Pythagoras theorem? Okay, so do you want to do that? What would this be? X. So 8 squared plus x squared is 100, is 10 squared. 64 plus x squared is 100. X squared is 100 minus 64, which is 36. X squared is 36. What's x? 6. And in this case, we just say 6, not plus or minus, because we're talking about a distance. Is that okay? So far, we've managed now in this equation to figure out that that's a 6. And with that mind done, we get the last one, b. We've solved that equation. Okay. Ah, yes. I don't know what happened there. Something funny on the page. Let me see your notes there. Have you got your notes there saying scenario 1 solution approach? Is that right? Is that right? Great. Okay. Let's take it from there. Scenario 1 solution approach. We have two sides and a right angle. So we're given two sides, an A and C in this case. We want to find the third one, and we do that. We could use Pythagoras, use the sines, use 180. So let's go through the questions. Question 1, we've B here and C here. How do we solve that question? We know that that's 90. So we've this and that and that. The lowest number they can give you are 3 things. They have to give you 3 things out of the 6. Is that okay? So you've got 3 of them here. Can I get this angle or this angle? Not directly. Can I get this fella here? Because of Pythagoras, is it? 8 squared plus x squared is 10 squared. And that gets me that. Okay. No. Example 2. Example 2, right angle triangle. You're given 2 sides and you're asked to find the angle A. You're told that this side here, you're given A, is 6. This one here is B, is 8. This is 90. And you're asked to find the angle A. How do you do that? Well, I promised you that this is the only toolbox you need. So it's going to be one of these three. A plus B plus C is 180. Do I know two of the angles? No. So I can't use it. Pythagoras, can I use Pythagoras? Well, yes, I could, but I'm actually interested in the angle A. I'm not interested in the length. So how do I get the angle A in here? Well, once I'm interested in an angle, what's the first thing I do? I draw a line across, and I call this side, what do I call it? Opposite. This side, the 90, I call hypotenuse, and this one here I call adjacent. Is that okay? I'm not interested in C, but I know A and B. In fact, let's put the words on them. What is this one here called, this A? It's called the opposite. What's this one here called? The adjacent. In other words, I know that the opposite is 6, and the adjacent is 8. Do you know any equation at all that links the opposite and the adjacent together? Where is opposite and adjacent linked together? Tan. Basically, it says that tan A here is opposite and adjacent. Is opposite over adjacent, which is 6 over 8. So tan A is equal to 6 over 8, or 0.75. But what am I interested in? A. So how do I get A? How do I get rid of the tan? Inverse tan. Tan is inverse tan 0.75. They cancel. A is equal to inverse tan 0.75. Can I put in 0.75 in the calculator? Yeah. Can I hit inverse tan? Yeah. What number will I get, by the way? What was the tan for 45? Do you remember? Every time I went out 1, I went up 1. 1. This is less than 1. Will this angle be less than 45? Yeah. The answer I get is I find a tan of, well, what I say is, I've said tan is opposite over adjacent. Tan A is 6 over 8, 0.75. A is inverse tan this. A is 36.87. 36.87. Less than 45, that's my angle. If I know that's 36.87 and I know that that's 90, what did the three angles add to? 180. Can I get this one? Yeah, just take it from 180. So example 2 now. Given two sides, find angle A. I had these two. I had the 90, and I now have A. So you now have angle A. Example 3. Similar type idea, but now you're interested in angle B. We don't have B. How do we find B? First step, always with an angle. What do we do? Opposite. Hypotenuse. Adjacent. Is that okay? We're asked to find the angle B. Let's look at what we know. We know that the adjacent is given as 6. The hypotenuse is given as 10. And the opposite, we don't know. Do you know any equation whatsoever that joins the adjacent and the hypotenuse? What calls adjacent and hypotenuse together? Cosine. So we look at and we say cosine is adjacent over hypotenuse. So cosine of B is this fellow here adjacent because it's near over the hypotenuse, which is here. So 6 over 10 is 0.6. So cos B is 0.6. How do you get rid of the cos? Inverse cos. B is inverse cos this. Type in 0.6. Hit cos 53.13. This angle is 53.13. That's how you do the question. Is that okay? If we know that angle, and we know the 90, we can get the other one by adding it to 180. So, finishing that example, we now know angle B, because we had the two sides. We've picked up the B and the 90. And we're making progress. Now, a relatively straightforward question. Finding the third angle. We know the three sides in this particular question, 6, 8, and 10. We know one of them, A, we're told is 36.87. This is 90. So what's this one? Well, forget the maths for the moment. If this was 30 and this was 90, what would that be? 30 and 90 would be 120 plus 60. Is that okay? This is slightly more than 30, so it'll be less than 60. Is that okay? How do we get it? Well, we just simply look at the only set of tools we know. And on this occasion, we're actually using the three angles rule. That's our toolkit. A plus B plus C is 180. So we can do this slowly. We can say B, therefore, is equal to 180 minus A minus C, taking this one over and that one over. But A we know as 36. C we know as 90. So it's 180 minus A, minus C, 53.13. So, finding the third angle, we now looks like we have it. You now have the third angle, and we're done. So you're given one and the right angle, and it's sorted. Okay. So let's go back to that page, if we can find it again. I think I called it the toolkit page. And really what I'm saying is that if you're to highlight that in some way, that is the only set of tools you need to solve absolutely every question on right-angled triangles. Is that okay? We'll either use the A plus B plus C rule, which you did last. We'll use Pythagoras, which we use a lot. Or we'll use these trigonometric functions because we knew the adjacent over the hypotenuse or whatever. Is that okay? And they all come out like that. Now, the last topic in session 1 is the right-angled compass directions. What they do in navigation is they don't use the cosines and the sines and the various angles that we're used to of starting here at 0 degrees and this being 90 and this being 180 and this being 270 and all of that. What they do is they do everything on the basis of north and south, particularly. Not east and west first, like x, y, but north-south first. So, for example, if they say something like N45 east, north 45 east, what you do is you go north first, and then you turn east by 45 degrees, and you end up here. Now, we would call that angle 45 degrees from 0, starting here around the clock. But they call that north first, and then back 45. If they wanted to go to 120 degrees, they would say north, and then over a bit, an additional 30. So they would say N30 west, because they're going in the west direction. This number here, S, 63.44W means go south first, completely, and then 63 degrees west. Now, this would be 270 to us. 60 would be about 210. So this turns out to be about 206 degrees there. But the last one I'll do, just to pick a point, maybe here. What would this be? We might call that maybe 320 or something like that. 320 degrees, leaving 40 left. But if there's 40 left, they would say that angle is basically south, completely first, S. And then we want to go here if there's 40 left, we want to go 50 towards east. So they'd say S, 50 east. And that's it. So they might throw a question like that. It's just a different symboling system. It's just so you can read a diagram. Nothing more complicated than that in it. Okay. I'm going to continue, take a few minutes. I'm going to do now trigonometry that's not right angle triangles. Is that okay? The normal stuff, trigonometry where they're not right angle triangles. I'm just going to take an A4 page to make sure that I've got the pages in sequence as I'm calling them out. Now, trigonometry, non-right angle triangles, or trigonometry part 2. What we're going to cover here are scalene or oblique triangles, some definitions and terminology, trigonometric rules, the general triangle toolbox, more sophisticated one, and some examples. So let's consider the general scalene or oblique triangle. It's just three sides. One is called A, one is called B, and one is called C. You can call them in any order you want, but most importantly, C must be opposite capital C with the angle on it. B must be opposite the B angle, and A must be opposite the A. And then all of the equations in the Formulae book, in the tables, they all work. Now, this is your toolbox for these questions. Pythagoras is gone because it's not a right angle triangle. The first one is that all of the angles must add to 180. The second one is a cosine rule that says that a squared is b squared plus c squared minus 2bc cosine a. And it's also written as cosine a is this. There are two versions of the cosine rule. One of them on the left-hand side, I'll call this the cosine rule for length, because what you're interested in is the letter A. Whereas this one, I'll call this the cosine rule for angle. Cosine. If we were just to take a moment on this, we would say that the cosine rule says that a squared is equal to b squared plus c squared minus 2bc cosine a. But if somebody said, I would like my focus to be on something different, I would like it to be on this thing, the angle bit, the cosine A. How would I do that? Well, I would just do it the way I've done it before. I might take this to the other side. So I would say a squared plus 2bc cosine A is b squared plus c squared. Just taking that over to the other side. Then I would take the a back to the other side, and I would say 2bc cosine a is b squared plus c squared minus a squared. And then I'd say, but that's just multiplication. So I divide by 2bc and divide by 2bc here. And I would say cosine A is equal to b squared plus c squared minus a squared over 2bc, which is the second part of the same equation. Is that okay? So even if you're only using one, you can turn it around into itself. The last one is the sine rule, that a over sine A, b over sine b, and c over sine c. So we've effectively got 3.5 things in our toolbox. The angles, 2 cosines, and a sine. All questions can be answered by those, every single one. So let's see how they start. Well, it starts off with solution approaches again. Here's an example where you've got 2 angles and you want to sort of go through. Well, how do you get the third angle if you know 2 of them? Is that a fairly straightforward one? The 180 rule? Okay. Here you've got 2 lengths, here A and B, and they share an angle. A and B and the angle C. What I mean by them sharing a length or sharing an angle is that if this is A and this is B, well then we know that that's going to be capital A, and we know that that's going to be capital B, so therefore this must be C. And A and B share C because it defines them. They don't share this one because A has that but B doesn't. They don't share this one because B has it and A doesn't. So this is called shared or common. So this equation here has 2 sides and a shared angle. And if you look at the cosine rule for it to work, the length you have you don't know, but the other 2 lengths you do know, and the angle must be the one that you don't have. It must be the shared angle. So this works for the shared angle between them, not just for an angle, but for the shared one. So it looks like we could use the cosine rule here, and we can. If you're given 3 lengths here, A, B, and C, you don't have any of these, where do you go? Well, you might look at this one and say, but I don't have to know an angle because they're all lengths. And if they're all on the right-hand side, the B, the C, and the A, I can get the cosine of the angle, so I can start. So that's useful for the cosine to get an angle. If I go further and say, given 2 angles and the opposite side. So what we're saying here is we've got 2 angles and 1 side. Well, we can obviously get the third angle, but we've got 1 side. This says you can use the sine rule. So 2 angles, say sine A and sine B, and 1 side. And the side is an opposite side. So in other words, it's either the A or the B. And here you've got 2 sides and an opposite angle. You've got A and B and the angle A. So unlike the last one where they shared, in this case I'm saying it's not C you're given, but you might be given A. One of them is opposite. Well, we'd use actually the sine rule for it. Okay? So we're now going to do some of those questions. I'm going to start with example 1. You're given 3 sides and you have to find the angle A. You're told B is 7, C is 8, and A is 5.814. So what I'm asking you to do is tell me, which of these do I use? Do I use 1, 2A, 2B, or 3? To solve that question, I've got the 3 sides, 1, 2, and 3 sides. In other words, I know A, B, and C. Which one would you go for? Which has the best picture on the right-hand side? And by that I mean, which one has the most things known about the right-hand side? So write down your pick, or whatever. I have to use one of these 4 tools. That's all there are. Well, am I going to use the angles one? With nothing known. Forget it. I'm going to use the next one, cosine rule, for A. Do I need even to know A? Sure, I know A. I know the length, so that's not in. The angle here, do I know the three sides? A, B, and C? I do. I don't know the angle, that's useful. Hey, I think it's that one. I'll go with that. Is that okay? So I'm going to use the cosine A now. So what I do is, I start looking at the cosine rule for it. And I say the cosine rule says this is the rule for the angle, because I'm looking for an angle. Cosine is b squared plus c squared minus a squared, so I multiply all those up. 7 squared plus 8 squared. Cosine A is 0.7071. But if I know that the cosine of A is 0.7071, how do I get rid of a cosine? Inverse cosine. So A is inverse cosine that. A turns out to be 45. So I've got 45. I now know another thing about it. If I look at I'm up here, I've ticked my A box. So in addition to the three sides, I've got my A, I've got my 45, I'm making progress. Is that okay? Next one. Example 2. I've got two sides and a shared angle. So in this particular question, I know that C is 8 and that B is 7. And I know that A is 45 degrees. And nothing else. Don't know any of the others. So I've got B and C and the shared angle, the one between them. So I go looking at the toolbox again. And which one are you going to pick this time? I know two sides and a shared angle. And I'm looking for something to help me move it along. Am I going to use the first one? No, because I don't know two of the angles. Two sides and a shared angle. Does this look interesting? Two sides, B and C, shared angle. That look right? This one here, the angle, I don't know the three sides. And this one here, there's loads of angles I don't know. So it's this one. It's the cosine rule for the length. So I start off and I say, let's look at the cosine rule for A. Well, I know C was 8. I knew this was 7. And I knew this was 45. But the cosine rule allowed me to find this one as 5.814. Because that squared is that squared plus that squared plus 2 that times this. So now I can find out what A squared is. And of course, when I get A squared, I find that A squared is equal to 33.8. But what am I interested in? The length, isn't it? So I know what A squared, what do I want? A, don't I? How do I get rid of the square? Square it. Is that okay? So I get A is 5.814. And again after that, here I am. Example 2, I had those before, but now I have the A as well. So I'm up to 4 of them from 3. Example 3. Two sides and an opposite angle. Two sides here, I've got C is 8. I've got A is 5.814. And I've got this 45 here. This 45 is opposite one of the letters. I don't have the shared one. The shared one would have been up here. And that's still unknown. What I have is an opposite one. So I started looking for that in the toolbox. Have I got anything for that? Have I got a screwdriver or a pliers or something? A plus B plus C is 180. That's great, but I actually only know one of the angles, so that's not going to work. A, I'm looking for a length. B, C, great. Two other lengths. And the angle, great. I'm looking for a length, which would be useful, that one there. Two other lengths I know, great. Oh, I don't know the angle in the middle. Can't use it. I don't know the cosine of B. I know the cosine of the other one, so I can't use that. Maybe the next one. Look for the angle here, cosine A. Let's go with that one. Let's see cosine B. Oh, I need to know the three lengths. All right, that's no good. What's this sine rule about? Okay, well, the sine rule says something like that A over sine A, B over sine B, C over sine C. Well, what do I know? Well, I know this A and sine A. I know the A and the angle. So I have the A and the sine A. That's good. On the B's, drawing a blank there. On the C, I've got one of them. But if I knew this bit, and I knew, say, half of that bit, could I finish it? Probably. If you think about it from a mathematics point of view, if somebody was doing ratios with you, and they said, 1 over 2 is 3 over what? You managed to find it. You say, how did you do that? Well, it must be over something. Let's say it's over x. Well, if it's over x, let's crisscross. X would be equal to 3 times 2, which would be 6. Oh, we found x. All right. Or you could say 1 over 2 is 3 over x. Well, I don't know what x is. See if I can solve it. Multiply by x here, multiply by x here. They'd cancel. Multiply by 2 here, and multiply by 2 here. They'd cancel. X is equal to 6. I'm still getting x equals 6. I can still solve it. So what we're saying is that it's worth going after this sine thing. Now the A over B, A over sine A, B over sine B, and C over sine C, it looks like I have A is known. I have C is known. Angle A, that's known. And as for B and C, don't know anything there. But if I went for the sine rule and just took this bit, A over sine A is C over sine C, I'd get A is 5.814 over sine 45 is 8 over sine C. Sine 45 is a number. That's just like a calculator. That's a number. That's a number. So I can work out the ratio. I can say that sine C, if I wanted, taking it up, this side, crisscross or whatever, and I can find out through crisscrossing it, by rearranging it, multiplying sine C up and all that sort of stuff, that sine C turns out to be 0.973. But what am I interested in? Sine C or C? I'm interested in the angle, haven't I? How do you get rid of a sine? Inverse sine. So C is 76.64. Once I know that angle, well, I'm up again. Because now I've got the angle A and the angle C, the sine C. If I know 2 of the angles, you reckon I can do the third one? So the last page basically says is that as you go round the block on these things, if you've got 2 sides and 3 angles known, well, you can find the rest by either the cosine rule, will tell you using either the lengths or the shared angle, the sine rule the other way around, and they were all the examples we used. Example 3 used the sine rule to determine the size of an unknown angle, and we could have done it for, like, if we wanted to now use the B, do you reckon we could calculate B here through the 180? And if we knew the B, could we get this one? How? Well, we could get it through the cosine rule, because we know the other 2. We get it through the sine rule because we know that over that is that over that. Whole lot of ways of getting it. So the remaining values then, we have 2 angles, would give us the third one, the third angle. The third angle is 58.36. And everything basically becomes fully determined. Is that okay? You're probably waiting for a break, are you? So, Yeah, I suppose we'll give you a break because we did start late. I've about 10 minutes to go on this, and that's it, on the sectors, okay? Or do you want to do it if people are... Will I kill this section? I'll kill this section for the 5 minutes, okay? And then, because you'll take a break, I'll be breaking by 4. Okay, trigonometry then, section 3. Section 3 is really only about one equation. It's about the area of a triangle. And there's formulae for that. Some examples and a sector. So there's a picture of a triangle. And we're interested in the area. Well, your toolbox now has changed again. And there are actually only two formulae for the area of a triangle. The first one is probably the most familiar, half the base by the perpendicular height. You've heard that a few times. Is that okay? But the other one, maybe less familiar, is that the area of a triangle is 1 over 2 times AB sine the angle in between. 1 over 2 BC sine A, or 1 over 2 AC sine B. So you can find that here. If I wanted to find the angle, the area of this whole triangle here, I say, well, if that's B, or that's C, and that's B, this is angle A, it's a half AB, or sorry, BC, these two, sine A. And if I know this angle, and I know these lengths, it's done. So example 1. What's the area of this triangle? You're asked to find out the area and see what you're given. You're told that this is 10, B is 10, to this point. And it's a further 2 afterwards. So the total length of this line here is 12. Is that okay? This length here is 12.81. That's C. And you're told that this angle here is 38.66. Which of the tools in your toolbox do you use? Do you know 2 of the sides and the angle in between? Do you know the length of side C and the length of the full length of this one and the angle in between? You do, I think, don't you? So the whole area is given by a half of, well, do I use AB sine C, BC sine A, or AC sine B? Which do I use? Well, if that's B and that's C, it's BC sine A, the middle one. Is that okay? And that's how I solve that area. So it's a half of 12, the total distance, times 12.81, sine the angle in between. That turns out to be 48. Now, could I have found the area another way? Well, half the base by the perpendicular height. What's the base? 12. What's the perpendicular height, though? Imagine that I didn't know that that number there was 8. Imagine if I didn't know what the perpendicular height was. But I knew that that was a right angle triangle there of 90. And I knew that this angle was actually given, and let's say the given angle was 38.66. If I know that angle, and I know this length here, do you reckon I could find out what that height is? Let me just draw this very simply as a puzzle. You've got this triangle. You're told it's right angle. You're told that this length here is 10. You don't know what this is, but you're told that this is 38 degrees. Could you work out what that is? If you knew nothing else. There are 3 things there. What type of triangle is it first? right-angled. Don't think we can use Pythagoras, can we? Because those two are missing. Is that right? Don't think we could use the angles. That would help us a bit. And if we had the angle here, could we get the other angle, do you think? Yeah. And that over that, on the sine, we could probably use, couldn't we? That over sine this is that over sine, whatever, that over sine that. We could use that, couldn't we? Is there another way of doing it without going into sine, all that stuff? Is this an angle of interest? Is it? What do we do? What do we call this side? Opposite, is it? What's this side here? Adjacent, because this side happens to be the hypotenuse, isn't it? Let's imagine that I'm looking for the value x. Do I know this number? Do I know that that's 10? Do I? What links opposite and adjacent together? What does? Tan. So tan of 38.66 is equal to x over 10, isn't it? Yeah? Is that a number? That's dividing by 10. How do you stop something when it's dividing by 10? Multiply. So you get 10 times tan 38.66 is x. Is that a calculator job? We found x. Is that okay? That's another way of doing it. Is that okay? So let's imagine that we then found that that angle was 8, or the height was 8. The area then is a half the base by the base, the full base by the height is 8/48. That's a picture of an equilateral triangle, 360s, shown with two lines or whatever, or a common marking, and the same angles. An isosceles triangle, two sides the same, but the others are not, but the two angles on the bottom are the same. The one between them isn't. Very straightforward theorems that if A plus B is plus C is 180 in the triangle, A plus B plus C give 180. What's this angle here? If that's a full angle on a flat line, that must be B. B plus E must be equal to what? 180. So if B plus E is 180 and A plus B plus C is 180, we could actually write that as an expression that says A plus B plus C is 180 is equal to B plus E. Or A plus B plus C must equal B plus E. Or A plus C must equal E, or E must equal A plus C. In other words, the external angle here, E, must be the same as the other two. Because whatever that doesn't make up of the 180, B does. And whatever that doesn't make up of the 180, B does. Very last question. Sectors of circles. Here's a circle, and it's made up of a small sector. The full angles in a circle is 360, like pizza, round thing like that. The perimeter is given in your book as 2 pi r. The area is given as pi r squared. If we look at this in fairly simple mathematics, and you take your standard pizza, that would represent half the pizza, the bit above the blue and the bit below the blue. And if you decided to split the pizza in 4, say that's a quarter, you'd have 4 of those. Very often pizzas might be split in 8 or in 6 or something like that. Okay? And there's your share of it. Now, how big is this section here? Well, it all depends on how big the angle is. What's the total angle in a circle? 360, isn't it? If this angle here was 90, how much of the pizza would you have? Quarter. Is that okay? Because if you think about it, crisscross, 90, 90, each quarter. Is that okay? So that's a 90 degree, if it is 90. If the angle was A, and you weren't hungry at all you wanted was this tiny bit here, you'd had your lunch or something, and that was only 10 degrees, how much of the pizza would you have? Well, you'd have 10 degrees over 360 degrees, or 1/36th of the pizza. Is that okay? Or if you wanted 180 and you felt really you hadn't eaten for a month, that'd be, 1/2. Is that all right? Now, the question came up, and that is, how would you work out the area of that? Or how would you work out the perimeter length? Well, let's look at first of all, the area of a circle. The area of a circle is given as, here, area. Area of this pizza is pi r squared. What about the area of the bit that you've had, which is only 10 degrees? How much of the pizza did you get? What did we say it was? 1/36th. It was 10 over 360. You'd get 10 over 360 the area. In fact, if you look at any sector here, it's defined by the angle A. So, what's the area of that sector here? Well, if it was 90, you'd say it would be a quarter of the pizza, wouldn't you? If it was 10 degrees, you'd say it was a 36th. If it's A, it's whatever A is divided by 360. Because if A is 10, it's a 36th. If A is 90, it's a quarter. If A is 180, it's half. And if A is 360, it's the whole pizza. So the ratio is just A over that. So the area is pi r squared as before times A over 360. The same equation applies to the length of the perimeter. If you go for a walk along the perimeter here, of the circle, and you're just going on a little bit of it, maybe just from Q to P, P to Q. Well, what's the perimeter of a circle anyway? Well, there's an equation for that. It's called 2 pi r. So the whole circle would be, perimeter is 2 pi r. How big is the length that's just A degrees? Well, if A was 90, would it be a quarter of the length? If A was 180, it would be half. If A was 360, it would be everything. So the perimeter length, again, is 2 pi r times A over 360. It depends on how big the circle is. Is that okay? So the question they ask, so here you go. There's the perimeter, and the arc is A over 360. The area, A over 360. It just depends on how big the A is. So this was the question they asked. And they said, here's a circle. Here's the sector. You bought yourself an ice cream cone. There's a bit of ice cream popping up the top there. And they said, how big is that area in green? Now, what you've got to do is you've got to figure out, and this comes up, you've got to look at it and say, they can't be bringing up new stuff just for the fun on the day of the exam. I must have covered this. So it must be something that I've seen before. And all of the questions in the paper will be something that you've seen before, just a bit of interpretation. But what is this shape? If you take the whole lot of it, this shape here, is that a bit of a circle, that thing? The total, isn't it? It's a lump of a circle. Now the area, if we're talking about area, is pi r squared. The extent of the area depends on this angle A. So if it's A over 360. So that tells us the area of the sector. We're interested in the green bit. But how do we get the green bit? If I took out the blue bit here, what's the blue thing? What is that shape? A triangle. It's a triangle. Okay. Do I know anything about it? Well, let's look. I know that the radius is 20. I know one of the lengths, and lo and behold, I know the angle in between. Is that okay? If I know the two lengths and the angle in between, can I work out the area of the triangle? Yeah, it's a half, one of the lengths by the other lengths by the sine of the angle. Now in this particular case it's 90. So it's a half, 20 times 20, sine of 90, anybody? Turns out to be 1, okay? So 20 by 20 is 400. By a half is 200. Okay? Another way of looking at that equation from the triangle point of view is that's a 90-degree angle, isn't it? That means it's a right-angled triangle, isn't it? That means that if I were to turn it around this way, it would look a bit more normal. And that would be a triangle on the flat. And that would be the base, and that would be the perpendicular height. So I'd get half the base, which is half of 20. And the perpendicular height would be 20, which would be 10 times 20, which would be 200. So I could solve it with either one. Now, what's the area that's left? It's the sector minus the triangle, isn't it? Because it's the sector bit minus the triangle bit. The sector we found was pi r squared. So let's look at that. The sector was, the area of the sector was pi r squared times a over 360. Pi is pi, or the radius, we were told, was 20. A, we were told, was 90 over 360. So effectively we got pi 20 squared over 4. That was 1 over 4. 20 by 20 is 400. 400 over 4, which is 100 pi. So the bit on the top, the fancy bit, okay, the non-overlapping section, in other words, the bit that's in the sector that's not in the triangle, is 100 pi for the whole lot minus the 200 for the triangle, and that's our answer.